UWIG Achievement Award from Utility Wind Integration Group, 2011 Distinguished Alumnus Award from IIT Kharagpur, India, and 2012 IEEE Power and Energy Society Ramakumar Family Renewable Energy Excellence Award. In 2013, he received the Innovative Program Award from the EC Department Heads Association, made up of over 250 US universities. In 2014, he received the Distinguished Graduate Teaching Award from the University of Minnesota and the IEEE Narayan Hingarani Facts Award from the IEEE Power and Energy Society. He is a fellow of the IEEE and the member of the National Academy of Engineering. Professor Ned Mohan sir is with us today to give us a talk on graduate courses in electric power, power electronics and electric drives with an emphasis on sustainability at the University of Minnesota. And he will also tell us about the ongoing research work in the field of electric power, power electronics and electric drives with an emphasis on sustainability at the University of Minnesota. Thank God, sir, we had the discussion this year itself. Otherwise, I would not have finished reading out the list of awards. You would have received more awards. Welcome, sir. Om Nam Shivaya.
Thank you.
We are so glad to see you.
Okay.
Wish you could have been here in person.
Yeah.
Shall we move on to showing your slides and showing your presentation?
Yes, please.
Sir, this is Ravi Shankar.
No, hi, Ravi Shankar.
Sir, would you like to address the gathering?
Well, thank you very much, Dr. Nair, for arranging this, my not panel discussion, but my talk. Unfortunately, I could not be there in person, but I really appreciate this opportunity. And so I have, as you mentioned, recorded these couple of video clips. And please, fast forward them where they're too long, because, one is about half an hour and the other one is about 20 minutes. So I really appreciate your taking the time to get together and discuss what we can collectively do when it comes to renewable energy, as we can all appreciate how important this topic is, as any topic, I would think. So with that, I will just keep quiet and listen to this.
One more thing I wanted to tell you. I have on my right side Professor Gopakumar of ISC Bangalore.
Yes, I know him very well.
Yeah.
And I also know Professor Shania.
Yeah, Dr. Shania on the left side, and Dr. Walter Sumitsu from Brazil, Federal University of Brazil. And three of them are here already.
Yeah, good afternoon.
Good afternoon.
And we have so many eager participants waiting for your talk.
Okay, good. Good to see you all.
Good to see you too.
Sir, right now we are moving to play your video as your keynote address for the IEEE TAP Energy 2015.
Sure.
So I'll be calling back for the question answer session after the video.
And I would like to begin by thanking Amrita University and Dr. Manjula Nair for giving me this excellent opportunity to talk to you. And in this presentation, I'd like to describe our curriculum development and also some of our research. So this is a beautiful view of our campus. It indeed is beautiful when it's not winter time. And you can see the river Mississippi flowing right through it. And our building is on the east side of this river. And so this slide is from NASA, and it shows a nighttime picture of the United States, and it shows that the metropolis of Chicago and Minneapolis, St. Paul are lit up, but it also shows that in the middle of North Dakota, where there are very few people living there are bright lights. So what are these? Well, it happens to be Bakken oil fields, where the natural gases that are accompanying this fracking, which produces oil, are being burnt off into the atmosphere. So, we are, developing oil, but are we doing responsibly? That is a big question. So there was an article in New York Times, which said that within 5 years we'll be, world's top oil producer, and I think that has already happened, as you'll see in the next slide. And so here's an article which was, on July 4th of last year, which says that U.S. indeed has become the world's biggest oil producer, overtaking Saudi Arabia. I'm not sure what has happened with recent drop in oil prices, but nevertheless, this is not a picture we are normally used to seeing of the United States. And so there is a great concern about the environment, and our Energy Secretary Chu is parting salvo. He says that, what would our children think? What we were doing, didn't we really care about the environment? So you see that these polar bears look worried. These polar ice caps are melting, and you're familiar with this hockey stick graph, which shows how the temperatures globally are going up. So with this as the motivational piece, we are developing a curriculum, graduate level, with sustainability as our focus, and also in part 2, I'll try to describe the research that is possible and what we are doing. So this is really the part 1 of this presentation. So in this, I'll describe the curriculum, and the outline is what are we doing, why are we doing it, and what are our plans to move forward in a collective manner. So I think there's a crisis in graduate education. We are simply not teaching the courses that we ought to be. And many courses are at the verge of disappearing due to 2 factors. One is lack of faculty to teach them, and also we need a critical number of students in each course to take them. Otherwise, it won't be economically justifiable to teach 1 or 2 students. So our objective is to develop a comprehensive electric energy education curriculum and enable all universities, and you can see here all is, emphasis is given, all universities to provide a first-rate education and again, and is underlined, and graduate students in large numbers. So that is really our mission. So here we look at sustainability and electric power in a holistic manner. So you see that we have electricity generation, transmission, and end use, and we should generate this electricity using as much as possible renewables, and then renewables are variable in nature, so we need storage. And then after we have generated this electricity, we need to use it efficiently, and also conservation is a big factor. Then when it comes to transportation, we have trains, planes, and hybrid and electric vehicles. So anything that moves requires power electronics and electric drives. That is, within the area of so-called power. And then also for defense, Navy, Air Force, and Army, there's a great need of these subjects. And then last but not least, the industrial competitiveness. When it comes to automation, robotics, advanced manufacturing, all these topics play a role. So very quickly, I like to just flip through these slides. There is nothing new that you don't know already, and you won't anticipate. So renewable energy, photovoltaics, and wind. And then when it comes to delivery, HVDC has a new topology called modular multi-level converters, MMCs, which I'll describe a little bit more in detail in the second part. And then when it comes to energy efficiency improvement, you see that this pie chart here, pretty approximate, it should be taken with a grain of salt, that motors, and if you combine motors used in HVAC, which is heating, ventilating, and air conditioning, we're talking about roughly 2/3 of all the energy being consumed, electrical energy that is, being consumed by motor-driven systems. And then lighting is a big chunk, and then also, in computers and other things, and IT, so to speak. So when it comes to motor-driven systems, here is a kind of a block diagram of a system where motor is directly driving the pump, and and this motor is fed from the AC supply, and therefore this motor runs essentially at constant speed, and therefore the pump is running at constant speed. And if you want to control the flow rate, we have to use this throttling valve, and by closing down on throttling valve, we can reduce the rate of flow, whether it's liquid or gas or whatever. But some of the energy that is being supplied by the motor is dropped across this throttling valve, which will get extremely hot were it not for the flow of whatever is flowing through that system. So, that's not a very efficient system. And so you see at the bottom here that instead of using that throttling valve, if you can control the speed of this pump efficiently using an adjustable speed drive, then we can make this overall system much more efficient. And of course, lighting is the development. We went from incandescent to fluorescent to compact fluorescent lamps, CFLs, and now to LEDs. So that has been the trend in lighting to make it more efficient. And then there has been a sort of a quiet revolution in wide bandgap devices. So silicon carbide and gallium nitride, for example, these are wide bandgap devices, and they promise to reduce the losses in these devices by a significant percentage, as shown here. And so they are now appearing on the market, and there's a very good chance that they will be used in future power electronic systems. So that's really somewhat revolutionary when it comes to power electronics and increasing its efficiency. And so next we talk about transportation. Here is a slide I got on the 787, shows the integrated system. And here you can see that there's a great deal of power electronics and electromechanical systems used all over the plane, so-called Dreamliner. And these are the so-called fly-by-wire planes. So we'll see more and more use of power electronics and electromechanical drives in these systems here. Then, of course, we should not forget about high-speed trains. And these are electric trains, and again, they will require the expertise that is covered in these courses. Talking about defense, here is an aircraft carrier, but anything that moves requires drives, and therefore power electronics and power systems. You can think of a power system in this ship application. So it's kind of a microgrid, if you will. And then when it comes to automation, once again, we see a great deal of applications of these here. But also in very small things like heart pumps, in your cell phone, for example, there's a great deal of power electronics there as well. So here's an example of harnessing energy in the wind, and you can see that on the top of the nacelle, you have this low voltage generator, and the frequency of voltages and currents produced by this generator depend upon the wind speed, and so it's variable. And then the power and current, they flow down the tower, maybe 300 feet, 100 meters, and then at the base of the tower you may have a power electronics converter, which takes a variable amplitude, variable frequency voltage, and converts it to a constant amplitude and constant frequency. In our case, 60 hertz probably, and India, of course, 50 hertz voltage, which is then stepped up with a transformer to 34.5 kV. So that 34.5 kV has sort of become the de facto collection grid voltage. So at this 34.5 kV in a wind farm, many turbines may be connected. Okay, so all that power is aggregated at 34.5 kV, and then by means of another transformer, is stepped up to, let's say, 161 kV, and it's then transmitted to the rest of the utility system. So here you can see that there is a kind of a combination, a marriage of electric machines, which is a generator, then you have power electronics converter, and then you have power systems, the transformer and transmission lines, and there are certain requirements, so-called low voltage right through. Even if there is a fault on the transmission system and voltage were to drop even to zero, the wind turbine should remain connected for a certain period. So that's what this low voltage right through graph is showing us here. So you can immediately see that when we talk about electric power, we are talking about just not grid level power, but we are talking about power systems, which include, of course, the generation, transmission, and end use, but also power electronics, electric machines and drives, and renewable energy and the environment. So these are four categories that we look at, and when we started to teach this, you can see here that there was great enthusiasm, and our enrollments kind of tripled. And you can see that these students are smiling even after a 50-minute of boring lecture. So apparently they like it. So just to very quickly describe what topics we are covering and what is involved. First of all, power electronics. It's an enabling technology. We have source on the left side, let's say, and the load on the other side. But you need a sort of a black box in between, which we'll call power electronics. And so we have developed courses on this broad topic, and there is a, on the first course we use this book, and also we have a lab, a hardware lab, which goes with it. When it comes to power systems, we take kind of a integrated view of this power systems. Quite often power system courses just talk about power flow and things like that, but we really start from the, what does it take to generate electricity, and then how it is, how we use transformers, how we transmit it, and then how it is used. So taking a simple 3-bus system as we see here, where bus 1 may be the reference bus, where the generator is connected, the main generator, so-called the reference bus, and then we have another bus and where another generator is connected. So this could be a PV bus, and then on the third bus we have it's a load bus, so it's a PQ bus. So just using these 3 buses, you have all 3 types of buses, and you can then describe how to calculate the power flow on this 3-bus system in a way that it can be generalized to N buses. So that's the approach that we have taken. So we have another book on this, and then there's a software-based lab that goes along with it. So the third one I like to describe is electric machines and drives. And here we take a more system-level approach. So we see here that not just electric machines, but we say that if this load here has to be driven from this electric source on the left, then this so-called electric drive consists of motor and then a power processing unit, which is power electronics, and then through the sensors we have a controller here. So this is a system for controlling the speed and position of this load perhaps, and so power is flowing through this board lines over here, and then we have a signal indicated by these thin lines over here. So we have again a book which is dedicated to this course, and then we also have a hardware-based lab which uses these small 42 volt motors that are specifically designed for this lab. And then we have a DSP-based controller that controls these motors here in the hardware lab. And here is a picture of this hardware lab that you can see here. And this lab that we have developed has been commercialized by a third party. We have no financial interest in it. And it's being used in over 100 US universities. Here, you can see this video going to this link over here that Professor Heath Hoffman is describing how he has adapted this lab and is describing it to this journalist over here. So what our approach is to put all this material that we are developing on this CUSP website. So, this CUSP website, if you go to this URL here, you can see you don't have to become a member. You just go to this CUSP website and you can download most of the material. Not all, but you can download most of it. And as of now, this number 171 is no longer valid. 211 universities have become members of it. And as I mentioned, that once you know this URL, most of it is free to download. And so the content of these courses consists of video clips for each lecture, their textbook. Of course, you cannot download the textbook from this website, and in-class discussion problems, labs, and homework problems. So these resources are really developed for.
It's okay. It's okay. I think we should stop and you should go and have a good Malabari dinner.
Actually, we have a conference banquet after this session.
On our campus, we also have a very good Malabari restaurant. So I think I'm not sure you have any questions, but you can always email me if you have any questions or any suggestions or any comments. So,
Edmohan sir, Manjula here.
Yeah.
Yeah. It's not a question. I wanted to thank you. And one point I wanted to tell is, we had a panel discussion. We were talking about a panel discussion just before your session started. Yeah, you were also wanting to join us before, and then it didn't happen. So that in that panel discussion, which was on how to transform electrical infrastructure in rural and urban India, Dr. Krishna Shanai was moderating the session, and some of us were members of the panel that we had. And towards the end, there was a lot of interesting questions from the audience about why industry motivated research or study is not happening in Indian universities. The research or the projects that we do in Indian universities, why it is not coming from industry directly. And what is the solution? This is one of the questions that we had, and none of us answered, because it's like two parallel lines without any bridging between the two. So maybe your CUSP program or the flipped classroom program, which you were discussing in part 1 of your presentation, where you were saying that all that the industry people and the academia together have designed your courses, is a good relevant thing that we discussed today, because that is what we ended up the panel discussion without it having any answer. There was no answer to that. So maybe your course, we'll look into that. We will discuss with, as you said, we will discuss with Dr. Venkatarangan, Vice Chancellor of the university, and see what is to be done about the CUSP program. And also the research that you are doing. We are thankful to your students, PhD students and MTech students, David I'm not able to pronounce the names correctly. Eric, Saurabh, Rohit, Ashish, Ruben, Siddharth, Suvankar, Dandikota, Krishnamurti and Karthik Iyer. All your students whose work you were so kind enough to share with us. Research work. We are thankful to you, sir. Thanks to your students too to let you share this research with us.
Thank you. Actually, one of the master's students, actually she is graduating in 2 months. She is from Amrita University, Sneha.
Oh, so, from Coimbatore campus it seems. Coimbatore, Dr. Shashi and Dr. Sindhu Tambati and Dr. Vijay Kumari are here and they are saying that she's their student. Vijay Kumari, please come.
Hello sir, I am Vijay Kumari. I was the one from Amrita University, Coimbatore, sir. And I was the one who taught power electronics, the basic power electronics for Sneha Narasimhan. And I wanted to work with you, sir. It is my long-term, it is a long-term wish for me. It's an opportunity and a platform I am utilizing. I met you in IIT Delhi, sir, once in the workshop. I discussed with you. That time I was doing my research. Now I have completed. I'm waiting for your call, sir.
Okay. You're doing a very good job teaching. You're doing a very good job teaching because she did a very good thesis work. She has built a silicon carbide based converter, and she is looking at these bearing currents. When you have very fast switching, you have stray currents which flow through bearings. Professor Gopakumar knows all about that. We are following his papers. So she is measuring it, and we plan to publish a proprietary journal paper. And so she gets finished this August, and she already has a job with Rockwell in Milwaukee. So obviously, you are doing a very good job of training students. So we are very thankful to you.
Thank you. And, humbled, sir.
Yeah. So we meet again sometime.
Sure, sir. She was informing me when she visited us. She discussed about your research and also her publications. Everything we had a very long discussion, sir, because it is my area. So I had a very long discussion with her. Thank you so much, sir.
Yeah. Now with silicon carbide and wide bandgap devices.
Yes.
And
higher temperatures.
Dr. Shania knows all about that. So there's a great deal of excitement about using these devices in power electronics and maybe perhaps going to higher voltages and higher power. So it's a very promising field. And so I think this question that Dr. Nair was asking about getting industry involved, that is a very difficult question to answer. That is something we face here. How does industry support us in our research? That's not very easy because they are looking at they have a pretty short-term view sometimes. They just want to make a product and make profits. So I think it's up to us as the researchers to define areas where they could participate and perhaps get intellectual property protection, and then perhaps to come up with some products which they can sell. And in India, I think I'm an Indian, so I know that there's so much potential. There's so much potential because there's so many things that can be done, right? So, and photovoltaics, as you know, there's no way to stop them. They are just growing up like crazy. Just last December, I was in a village called Byas. So Byas is a river in northern India, but there's also a town called Byas. And there I saw India's largest rooftop photovoltaic system, 7.5 megawatts. So it's, they were it was some company, I think in Mumbai or Pune, that was responsible for installing it. But of course, the panels and the converters, they came from, I think, overseas. But that's a type of thing that research could be done. It could be more indigenous, So there's a lot of potential for applying power electronics and in renewables.
Yes, sir. When I saw your slides, one of your PhD student working on high frequency transformer link for interconnection, just I ventured into that. I thought of venturing into that, and I've just identified for one of my MTech students. I felt so happy to see that slide, sir. I'm not too much away from the field.
Right. No, I think there's MMC-based power electronic transformers. There's multi-modular converter-based power electronic transformers. I think applying them for combining power electronic transformers and drives, that's a very good idea. I didn't think of it, but it's a very good idea. And this student that I have, Ashish Sahu, he is from, I think, from Trichy. There's an NIT at Trichy, right?
Yes.
So he is a graduate of NIT Trichy. And so he is a fantastic student. So, I encourage you to follow the publications of him, Ashish Sahu. He's got a summer internship at Apple in California this summer.
Okay.
But he'll be back in November, and then we start again. So we should keep in touch.
Yes, sir. Yes, sir. Sure. I was looking forward for 12th name as Neha's, but thank God you've told orally, sir. I was hunting for Sneha's name in the list, but it was missing.
Well, maybe Ravi Shankar, I don't know if he showed the master's students. So she's not a PhD student.
Yes,
so the second slide I had, her name is there.
Thank you, sir. Thank you so much. Nice talking to you, sir.
Okay. Nice to talk to you.
Any other questions, interactions? Sir, probably I can send the video link to all the delegates of the conference. Shall I do that?
Yeah.
Okay, thank you, sir. So I can mail the video link that we have played here, and you all can probably go through the video later on, and you can probably talk with Dr. Ted Mohan, sir, either through Skype or emails. Okay, thank you, sir.
Thank you. Thank you.
Thank you, sir. Wish you could join us for the Malabari dinner after this.
Okay. Thank you.
Next time.
I'll have it here this afternoon myself.
Okay, so meet you during Tap Energy 2017.
Okay. Sounds good.
Thank you so much, sir. Thank you.
Yeah. Thank you.
I'm sure.
Bye.
Bye.